This symbol right here is the Greek letter chi. So it's spelled like, it looks like chai, but it's pronounced chi, like Kai, chi-square test. And this is called a goodness of fit test. And the reason it's called a goodness of fit test, we're basically comparing our data that we have to some standard that's already been set. So in the example from the last time, we had M&Ms, and we were seeing if M&Ms actually, if our bag of M&Ms fits the colors as designated or produced by M&M Mars. And it is a fact, they don't just make equal amounts of each color. They try to get the most pleasing to the eye color combination. And so they realize that they need more blues and oranges. You know, there's more blue, orange, and green than there are yellow, red, and brown. And they do change that occasionally, okay, what the color combinations are, the percentages. But this information was actually taken off of M&M Mars website, the percentages that they make. So, so we're seeing if our observed values from our sample match, how closely they match the values designated by M&M Mars. And the way we do that, we can't really use any of our other tests because we're using categorical variables like colors, orange, green, red, blue, yellow, and how many. And these are called counts in each thing. They're called counts. So we have our observed counts that we get from our sample and our expected counts, which is based on what the past says, what the company designates. And in today's example, we're going to be looking at birth dates of hockey players making it into the NHL. This is actually in a book called Outliers by Malcolm Gladwell. It's a pretty good book. It's not just about math, but it talks about outliers, you know, people who do things a little bit differently and how they've become successful doing it. So he suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. And specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from, players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if this is true, a random sample of National Hockey League players was selected and their birthdays were recorded. Overall, 286 were born in the first quarter of the year, January, February, March. 278 in the second quarter, April, May, June. 221 in the third, and 180 in the fourth quarter. Does this data provide convincing evidence that the birthdays of NHL players are not uniformly distributed? Okay, so one would think that if it didn't matter, I mean, who would even think that birthdays have anything to do with going into the NHL? Would you even think that to start with? If you didn't know that little tidbit at the beginning, you wouldn't even think about it. You would think it shouldn't matter when your birthday is. You have equal chances of making it into the NHL, right? The American dream, the Canadian dream, I don't know. So everyone should have an equal chance, right? Well, they're saying it's not an equal chance, basically. They're saying you have a better chance if you're born earlier in the year, okay? Because then, you know, if you're born like January 2nd, you can't go and start playing hockey until the next year. Somebody who's born December 31st and you're born January 2nd, even though you're only 2 days apart in birth, the person who is December 31st, they're going to obviously turn whatever age you can start playing hockey. What is it, age 3? I'm not sure. I know they start them really young, 4, I'm not sure. So they could start when they're 4 and you can't start until you turn 5 and you're almost 6. when you can start. So does that make sense that you would be bigger than most people if your birthday's early on in the year? Because you have to wait an extra year before you can start playing. Okay? I mean, that happens in school sometimes. Some people in the class are quite a bit older, almost a full year, sometimes even more older than other people who are very young. So in this case, it gives them an advantage. This is what we're saying. Now, not uniformly distributed means that there's not an equal amount born in each quarter of the year. Okay? So it does look like that because there's more born in the first and second quarter than in the third and fourth. So we're going to do a chi-square test for goodness of fit. How well does this data, and I'm going to have you focus right down here on this table here. This is a two-way table, and this is the type you have to make on your chi-square test. You need to provide this information in your test. And you can do it at the beginning, you can do it down here in the conditions, but the conditions is an ideal place to do it because of the large sample size. And we'll talk about that in a minute. So our observed values, we've got 4 quarters of the year, and these are the observed number of people who were born in each quarter, 965. The expected, the way we come up with the expected here in this scenario, not every scenario. The expected values are different. We did different expected values in the M&M video. But the expected values here, out of 965, shouldn't there be an equal amount in each quarter? There should be, if they're uniformly distributed. So we just take 965 and we divide it by 4. And that gives us, that's how this number. This is what we would expect to be born in each quarter. This is what we observed. The chi-square test is, we are deciding, the chi-square test is going to decide for us, are these differences from these values statistically significant? Are these values far enough away from here that we can say that they are not uniformly distributed? Or are they, you know, there's obviously going to be variation if you just take a sample, or are they so close, you know, they're close enough that we can't really say, I mean, they are uniformly distributed. So, anyways, we go up here. At first glance, it appears that the distribution of birthdays is not uniform since the observed counts are not all the same. Okay? Now, in the M&M example, it would be, you know, because our observed counts don't match the expected counts because there were different percentages. Okay, it is possible that the distribution is uniform and the differences we see were due to sampling variability. Okay, this is very similar to any other test we've done. We have different calculations and a name of the test. So to decide this, I will use a chi-square goodness of fit test. And you pick an alpha level. We still have a null and an alternative hypothesis. Okay, the null hypothesis here is that the distribution of birthdays in the NHL is uniform. And the alternative is it's not uniform. And that's based on what they ask us up here.
It's not numerical values anymore, or null and our alternatives going to be more wordy.
Yes, they're going to be, yep, words. Okay, so now we have conditions. These are very similar conditions that we had before with our other tests that involve samples. So is this a random sample of NHL players? Yes, it's stated. They told us that. Is 965, we're going to assume it's less than 10% of the number of NHL players. Over time, I mean, maybe not at one given time, but over time there have definitely probably been more than 9,650 NHL players on all the teams since it started. That's probably a fact. And then large sample size. When you're dealing with a chi-square test, any type of chi-square test, all of the expected cell counts are more than 5. So the expected cell counts here, they're all more than 5, and you have to provide that expected counts. We had to do that same thing back in the M&M's example. We had to provide, these were our observed counts. Our expected counts came from taking 50 times, well, there should have been 24% blue, so we took 50 times 24% to give us 12 blue. 20% times 50 to give us 10.8. Okay, so our null here would be the observed counts are equal to the company's claim, and the alternative is the observed counts differ from the company's claim. So I want you to be sure you don't misunderstand this one example here. Okay, you had to watch the video too. There are different ways to write the null and alternative hypothesis. There are different ways to calculate the expected value. It's all based upon what they're asking for in the question and what type of data you have. All right, so to calculate the expected counts in this example, we divided the total into 4 equal parts, uniform. And if this condition is not met, you should combine categories until they're all greater than 5. So if you have expected counts that are less than 5, you need to combine categories together. So like if these were, one of these was less than 5, you'd like combine these two and go by halves of a year. And that's kind of what you have to do until all expected counts are greater than 5. That's how you make the conditions be met. All right, so now we need to do the calculation for the chi-square statistic. The chi-square statistic, the formula was given back on the other notes. The chi-square statistic, chi-square is equal to the observed minus the expected quantity squared divided by the expected, and then you add all of those up. It's got a sigma symbol in front of it. So you take every observed value, so 286, minus the expected that goes with it, square it, and divide by the expected, plus the next one would be 278 minus 241.25 quantity squared over 241.25. So I get my chi-square value is 31.1492, and the chi-square has its own distribution that we talked about in the last notes. The chi-square distribution is in your notes, but you can use your, I'll show you how you can use your calculator. But you've got degrees of freedom here. So we talked degrees of freedom we talked about in the last set of notes again. So it was right here. Okay, so the t-distribution, chi-square distributions are continuous and determined by degrees of freedom. The degrees of freedom is the number of categories minus 1. Okay, and basically the picture, the shape of the graph is determined by the degrees of freedom, and the mean is the degrees of freedom, and the peak, in other words, the highest part of the graph, is the degrees of freedom minus 2. But degrees of freedom is the number of categories minus 1. So in this case, we have, the total doesn't count as a category. So we have 1, 2, 3, 4 categories minus 1. So the degrees of freedom is 3. And what we're looking for, once we have the chi-square value, we need to find what's the probability that our chi-squared value is greater than 31.1429. Now, you don't even need to write that kind of thing down, but that's what you're finding. You need to find out what's your p-value. Okay, every test gets a p-value that goes with it. So you're going to do second distribution. Yep, you're going to look for, so second distribution. It's right there. It's chi-square CDF. Chi-square CDF. Your lower bound is always your chi-squared value, 31.1429. Your upper bound is infinity. Your degrees of freedom. And it gives you, now this, it looks like 7.9, but it's to the negative 7th. So your p-value here, your p-value is going to be 0.12345, and then an 8. That's your p-value. Pretty much 0. That's your p-value. So you compare it, your p-value to alpha, p-value of 0 compared to alpha of 0.05, it's less than. So what are we gonna do?